Hello everyone, welcome to my channel. Now in this video we are going to understand a term called electric flux. Okay, now to understand this term electric flux we need to have some prior knowledge about a term called liquid flux. Okay, now liquid flux, it is also called rate of flow. Rate of flow. Okay, so now see, in class 11 we have seen, like, if you have a pipe, okay, and let's say A is the area of this pipe, cross sectional area, and the liquid which is flowing through this, it has velocity v, it is flowing in this direction. Then the rate of flow, it is given by the product of this area and the velocity of flow. Okay, now let us change this situation a bit. Like, now suppose we have a container. Okay, this is a container and this container is open from the top and this area is A. Okay, area of cross section is A. Okay, now liquid is falling in the vertical downward direction with velocity v through this opening part. Okay, so again, what will be the rate of flow? Rate of flow in this case, so as in this case it is product of area and velocity, here also it will be product of area and velocity, so it will be A into V. Okay, okay, now let us change this situation a bit. Like, same container, okay, this is the normal to the area, this is the area A, okay, but this velocity in this case, for this case, instead of coming in the vertically downward direction, suppose the velocity it is directed in this direction. Okay, and this angle is theta. Okay, so this V, the component of V in this direction, vertically downward direction, it will be V cos theta. Okay, so if you compare this logic, then here the rate of flow will be A into V cos theta, because now V cos theta is normal to the area. Okay, so here the rate of flow is A into V cos theta. Okay, now let us apply this concept to understand electric flux. Okay, now suppose you have some area A, this is some area A. Okay, and in this region the electric field intensity, it is directed in the upward direction. Okay, so these are electric field lines. Okay, and this is directed in the upward direction. Okay, so now we can say that this is the number of lines which is passing through this area. Correct? Now what happens if I change? So here the electric field intensity is normal to the area. Okay, now if I change the direction of electric field intensity, keeping the area same, and then what happens? See, now if the electric field intensity, it is directed in this direction. Okay, same electric field. Okay, but I have changed the direction of electric field intensity. Okay, so obviously the number of lines, see, this electric field I have represented with the help of electric field lines. Okay, and we know that electric field lines are used to represent the electrical environment surrounding a charge. Okay, so in a region where electric field lines are close, you have strong electric field. In a region where electric field lines have wide separation, you have weak electric field. Those things we know. Okay, now based on that we are going to understand this term electric flux. Okay, so now see, here the number of lines which are passing through this area, now on changing the direction of electric field, now fewer number of lines are passing through the same area. Okay, fewer number of lines are passing. Okay, that is because of changing the direction of electric field. Okay, now similarly, what happens if I keep the electric field same? Okay, but if I change the orientation of the area, okay, if I change the orientation of the area, again the number of lines which is passing through the area, it is going to change. So the basic concept is like either you change the direction of electric field, or you change the orientation of the area, or you change the magnitude of area. That is, if I reduce this area of this sheet, okay, or this area, if I decrease the area. Now in this case, if I decrease the area, reduce the area, then the number of lines which are passing through that smaller area is going to reduce. Okay, so that means the number of lines which is passing through the area, given area, it depends on the orientation of the electric field or the direction of the electric field. It depends on the orientation of the area. It also depends on the magnitude of area. Okay, so with regard to area, there are two factors which are deciding the number of lines which are passing through the given area. One is the orientation of the area, and the second one is the magnitude of the area, whether the area is small or whether the area is big. Okay, so now we know that for any physical quantity, if we need to, if the effect of changing direction changes the physical quantity, or if the effect of changing the magnitude changes the physical quantity, then it means that the physical quantity depends on two factors. One is magnitude, the other one is direction. Okay, so from that logic we can say that area is a vector quantity. So both in electrostatics and in magnetism, we will be treating area as a vector quantity, though area is a scalar quantity, but here in electrostatics and in magnetism, we will be treating area as a vector quantity, because here, as we have seen, that when you are changing the orientation of the area, see, if I have rotated the area, then the number of lines which are going to pass through the given area, it is going to change. Now similarly, if I reduce the area, the number of lines which is passing through the area, it is going to change. Okay, so I have not yet defined electric flux. We are just going to approach the concept of electric flux. Okay, so since this area, it has both magnitude and direction, so it means area is going to be treated as vector. Okay, now a vector has got a definite direction. So how do we define the direction of area vector? Now for that, we will be using this convention, like for closed surface. Okay, for closed surface, what do you mean by a closed surface? Like objects which are 3D, three-dimensional object, like suppose you have a cube. So this is a cube. Okay, so now for this surface, okay, so area will always be in the normal to the area, normal to the surface being considered. Okay, but in which direction? It will be in the outward direction. So for this surface, area will be in this direction. For the upper surface, area will be in this direction, upward direction. For the lower surface, it will be in the downward direction. Okay, so for closed surface, the area vector, for closed surface, the area vector will be normal to the surface but in the outward direction. Okay, and for open surface, what do you mean by open surface? Open surface means, like closed surface is three-dimensional object, open surface like in 2D, like a sheet. So suppose this is a plane sheet, and electric field intensity, it is directed in this direction. Okay, now again, as we have seen, that area vector is always normal to the area. So like for this sheet, area, normal can be in the upward direction, normal can also be in the downward direction. So we have to take that direction in which we have the electric field. Now electric field intensity, it is in this direction, so normal will be taking in this direction, the upward direction. So this is the area vector. Okay, so area vector is always normal to the surface being considered. If it is a closed surface or a three-dimensional object, it will be normal in the outward direction. If it is a two-dimensional object, it is in the direction of the electric field, normal to the surface in the direction of electric field. Okay, if the electric field is in the downward direction, if it is in this direction, then area vector will be normal to the plane in the downward direction. Okay, so now based on this, how can we define electric flux as we have defined liquid flux? Like suppose this is an area, okay, and this is the direction of electric field, and this is the area vector. Okay, so this, suppose this angle theta is the angle between the direction of electric field and direction of area vector. Okay, so if this is electric field intensity, this is theta, this component will be E cos theta. So E cos theta is the component of electric field which is normal to the area. Okay, it is normal to the area, and area vector is also normal to the area. So both A and E cos theta, they are in the same direction. So the flux, so this area denoted by the symbol phi, it will be product of these two quantities. So this is A into E cos theta, A into E cos theta. Okay, now similarly for the same area, okay, this is the area vector, this is the direction of electric field, and this angle is theta. Theta is the angle between the area vector and the direction of electric field. Okay, so if this is A, this will be, this is theta, so this component will be A cos theta. A cos theta is the component of area vector in the direction of electric field. What does it mean? See, this area, for this area vector is in this direction, so that means I have taken a component of this area in this direction, for which you have A cos theta perpendicular to this area, okay, for this surface. Okay, and for that particular surface, can we say that the electric field intensity is normal to this component of area? Yes, correct. So again we are taking the electric field normal to the area. See, here also I have taken the E cos theta, okay, and E cos theta is normal to this area. Okay, and here what I have done, I have taken the component of area in this direction, so that the electric field intensity or the electric field lines are normal to the area. Okay, so here I will be taking this A cos theta, product of A cos theta and E, to get the value of phi. So electric flux phi, in this case it will be A cos theta into E. Okay, so the idea is either you take the component of electric field in the direction of area vector and then multiply the two quantities, or you take the component of area vector in the direction of electric field and then multiply the two quantities to get the electric flux. Okay, now from this I can generalize the expression for flux as phi is equal to E dot A, or I can write it as phi is equal to EA cos theta. Okay, so this is the expression for flux. So phi is equal to EA cos theta. Now see, if theta is equal to 0 degree, if theta is equal to 0 degree means this angle is 0 degree, that is E is in the direction of area vector. Okay, now do note down that, see, this theta is equal to 0 degree, but we will say that electric field intensity is perpendicular to the area, because area vector is also perpendicular to the area. See, if theta is 0, that means this electric field intensity is, it is in this direction, and this is the area. Okay, so electric field intensity is perpendicular to the area. So in that case, theta will be 0 and this flux will be maximum, and it is equal to EA. Okay, this is the maximum value of flux. Okay, now in case theta is equal to 90 degree, if theta is 90 degree, that means electric field is in this direction, and area vector is like this. Okay, electric field is in this direction means it is parallel to the area, and when electric field is parallel to the area, the flux is 0. Yes, it will be, because when electric field is parallel to the surface, no field lines are passing through the surface. Okay, so this is the basic idea of flux. So see, remember, when we are calculating the flux, we are taking the electric field perpendicular to the area, okay, or we are making the area such that the electric field becomes perpendicular to the area. So in electric flux, we are defining as the number of lines which are passing through the area, and the area being held perpendicular to the direction of electric field intensity. Okay, electric flux as a number of lines which are passing through the given area, and the area being held perpendicular to the direction of electric field intensity. Okay, but remember that electric flux it is not the number of lines. Okay, it is just a figurative comparison for electric field lines. Like, we know that electric field lines are imaginary lines. Okay, they are not real lines. Okay, this is just the idea to compare the electric field or for two different charges. Okay, so this is the basic idea of electric flux. Some additional concept like phi is equal to EA cos theta. Okay, this is dimensionless quantity. This is dimensionless quantity. This is meter square. This is Newton per coulomb. So this electric flux will be Newton meter square per coulomb. Okay, so this is the unit of electric flux. Okay, and electric flux is a scalar quantity. Okay, it is a scalar quantity, and electric flux, don't confuse electric flux with just the number of lines. Okay, it is the concept of visualizing the number of lines associated with a given charge. Okay, and this, as we have seen, like flux, it is product of E dot A, dot product of E and A. So this flux is related to electric field. Okay, now electric field, it is related to a charge. So that means the flux is also related to charge. So that relation was given by Gauss's theorem. So I am going to make a separate video for Gauss's theorem. This video was based on for electric flux. Hope this video clarifies your concept with regard to electric flux. My best wishes to you. Good luck for your examination.